Hi guys, welcome to our chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at what complex numbers are and how they are applicable to us as engineers. So if we just take a quick look at the overview, we are first going to look at what a complex number actually is, along with what's called its conjugate. We'll then look at how to solve what would necessarily be deemed an impossible quadratic equation. We'll then take a look at what we call the Argand diagram, and then we'll finish this off with looking at what's called polar form. All of these are critical elements in the understanding and applications of complex numbers. So the first question that we have to ask ourselves is, what exactly is a complex number? Well, a complex number is essentially a combination of a real number and an imaginary number. So perhaps up until this point you are really only familiar with the idea of real numbers, but we do have something called imaginary numbers. Now a real number is what you have been used to since primary school, and a real number is any infinitely quantifiable value that essentially can be processed using a calculator. Whereas an imaginary number is one that is expressed in terms of a negative square root. Now we need to further understand what an imaginary number is and how these two relate to creating a complex number. But there's typically, when we talk about the imaginary number, we usually denote it by the letter I. Now there's two key ways in which we can represent the imaginary number. The first one is that if we end up with the square root of a negative number, -1, then that would be the letter I. Because if you try and do the square root of -1 in a calculator, you will get an error. And what that tells us is that this value is not a real number. It cannot be processed on a calculator. But that's not to say that it doesn't exist. It's just it doesn't work on real number scale. Now the other way that we can express this is that if we take the opposite of a square root, which is a square, then if we get the square of I, that would be equal to -1. So these two interchangeable relationships is what we need when we start to solve and simplify complex number equations. Now this is all very well in defining what an imaginary number is and also defining what a real number is. But the question becomes, well, what exactly does a complex number look like? Is it a single value? Is it the composition of both terms? Well, the way that we define a complex number is we usually have it in the form of z. So we say that z is equal to something. And the most typical way that we express a complex number is in this form. So we have z is equal to a plus bi. Now how do we distinguish between the real part and the imaginary part? Well, the real part is the term that doesn't contain the I, because remember the I denotes the imaginary element. So the A is the real section and bi is the imaginary section. So you can see that the complex number z comprises of the real section and the imaginary section. Now a and b are both real numbers. So even though the second term is the imaginary section, the value of b is still a real number. So that's the key point, is that although we say that this is the imaginary term, it still comprises of a real quantifiable number. Because if it didn't, then it would simply be impossible to solve. Now, this idea of that everything in maths has an inverse or it has an opposite. For example, the opposite of plus is subtract. The opposite of multiply is divide. And so in maths there is always the inverse representation of a given operation or a given type of value. And complex numbers is no exception. Because in complex numbers, the opposite is known as the conjugate. Now the conjugate is often denoted by z bar, and it has a little line on the top. So if this is our complex number, z is equal to a plus bi, then its corresponding conjugate would be z bar, so that's how we know this is the conjugate, is equal to a minus bi. So the key distinction here is that for the conjugate, the real part remains the same. The thing that changes is the imaginary part. In that the sign, so if this was negative, this would become plus. If this is plus, this becomes negative. So what we're saying is that the conjugate has the opposite sign on the imaginary section. The real section doesn't change, it's only the imaginary section. Now let's see why we need complex numbers in the first place and how they actually developed. Because without going too deep into the theoretical side of complex numbers, the best way in which I found resonates most with students is if we relate this to a simple quadratic equation. Because given this quadratic equation here of x squared minus 3x plus 4, on the face of it, it looks fairly standard. But we know from quadratics that our roots of the equation has three possibilities. We either have real and distinct, we either have real and equal, or we have no real roots. Now the quickest way of determining this is using the discriminant. So the discriminant will allow us to check whether or not this equation can be solved. And so if we take the discriminant, now the value of a is going to be 1, the value of b is going to be minus 3, and the value of c is going to be 4. That's just the coefficients of the quadratic. So if we pop them into the discriminant and we begin to solve, we end up with a value of minus 7. So what this tells us is that because b squared minus 4ac is less than 0, we have no real roots. So what that tells us is that from the standpoint of just the equations, this would tell us that there is no solution to this problem. But if we were to graph this, then you can see that the graph shows that this quadratic equation exists. But if we process it using the quadratic formula, it tells us it doesn't exist. So we have a bit of a contradiction. And this contradiction is what led to the development of complex numbers. It's because in this realm, we are saying it doesn't exist, but we can graph it to show that it does exist. So that means there has to be a way in which we can use mathematics to represent the equation of this particular quadratic. And so through years and years of development, the theory of complex numbers was able to identify and solve these quadratics whereby we have no real roots. Because the key word here is real. We don't have real roots, we actually have imaginary roots. And that's the key distinction. But let's just see how you solve these complex numbers in the most basic form. So say for example we had z is equal to 2 plus I. Then if we want to determine z squared, how would you go about this? Well, we know that z squared is simply z times z. So we have two brackets multiplied together. If we multiply these out, then we end up with 4 plus 2i plus 2i plus I squared. Now hopefully your eye is drawn to the I squared, because from the beginning of the lesson, we've seen that I squared is in fact denoted by minus 1. So we can replace I squared with minus 1. And therefore we do 4 minus 1 is of course going to give us 3. 2i plus 2i is going to give us 4i. So that's how you would solve very, very simple complex number problems. And this methodology is what can be used to apply in the quadratic sense, because up until that point, that quadratic equation was impossible to solve. Whereas now, with the inclusion of complex numbers, it can be solved. Now that then leads us on to the Argand diagram, because when we think about the idea of plotting x versus y on a normal coordinate system, we call this a Cartesian set of coordinates. So i.e. both axes are real values. X and y are both real. So that's what we call a Cartesian set of coordinates. Now, because a complex number contains a real and an imaginary section, we can't use Cartesian coordinates. We have to then use the Argand diagram to graphically illustrate the complex number. But in order to do this, we need two key variables. We need what's called the modulus, and we need the argument. And these are two key critical parameters that we need in order to plot the complex number on an Argand diagram. Now, the modulus simply tells us the distance or the size of the complex number from the origin, because one of the key characteristics of any complex number is that it always starts at the origin. So in every Argand diagram, your complex number will always start from the origin, and it can go in either direction. But the modulus will tell us the size of the complex number, and it is denoted by this equation here. Now, hopefully you will see some similarities between the modulus of the complex number and the distance formula of the equation of a straight line, in that we square both of the coordinates and then we add them together and take the square root. And that then gives us the modulus, because it's basically the distance the complex number travels. But then the question becomes, well, in what direction does it go? You know, does it go in this direction? Does it go in that direction? How do we know? And that's where the argument comes in, because the argument will tell us the angle that it makes with the positive x-axis. So we know that this is the positive x-axis in this line here. So that's our x-axis. Now, if we worked out that the complex number, the argument, was 90 degrees, then that would tell us that it would be 90 degrees from the x-axis in the positive direction. So your complex number would actually move that way. And this is denoted using, there are a couple of different nomenclatures that you use. For me personally, I either use the acronym ARGZ or theta. But either of these is acceptable, it's just a nomenclature. The key thing here is the right-hand side of the equation, which is the inverse of tan with the y-coordinate divided by the x-coordinate. And we will always have these, because the x-coordinate is the real part. So if we had, say, z is equal to, 3 plus 4i, then x is going to be equal to 3, and y is going to be equal to 4. So that's how we read the x and y values. Now, graphically, what does this look like? And this is really, really important, because this allows us to visualize the size and the magnitude of these complex numbers. It gives us more context. And a typical schematic would look something like this, whereby our x-axis is the real number, because remember, if we said the 3 plus 4i, this is the x-coordinate. So that has to be the real axis, whereas the y-coordinate is the imaginary section. So our complex number graph, i.e. the Argand diagram, tells us that the real number is on the x-axis and the imaginary number is on the y. So you can now see it is not a Cartesian set of coordinates. Now, r here is our distance. So that is our modulus of the complex number, and then the angle here is our argument. Now you might say, well, how come you have 2? Well, here this just illustrates that the conjugate and the respective complex number, because the top line here is the complex number. This line is the conjugate. You can see that the x values are the same. The only thing that's changed is the y values. And so the argument will remain the same. That's not going to change. The only thing that changes is that instead of it being the positive y value, it will be the negative y value. And so when you know one of these, you will always know the other. Now, if you want to know more about complex numbers in a lot more detail, then we do have a fully comprehensive mathematics course specifically designed for engineers that goes into a lot more detail in this. I'll put a link in the description to that, and you can check that one out if that's something that you are interested in. As well, you can always send us requests, and we can look at making more detailed and in-depth videos if that's something that you will find useful. But now the final part that I want to come on to is this, what's called polar form. Now, polar form is just a different way of representing the equation of a complex number. And it's essentially the algebraic representation of the line in the Argand diagram. So say we didn't want to draw the diagrams, say we just wanted to know what the equation is, then we can express it in polar form. And the equations that we're going to emulate here is that the general equation for polar form is as follows. We have r, and then we have the cos of the argument plus I sine of the argument, both of them added together, multiplied by the modulus, which is r. And you can see here it still holds the same form, in that the cos is for the real part, and the sine is for the imaginary part. So it still keeps that same form. But again, we won't go into the mathematical proof of that. That's out with the scope of this particular lesson. But again, if that's something that you're interested in, then please let us know in the comments, and we can certainly look at doing some mathematical proofs if that's what you're interested in. Now, that's just a reminder, is that r is equal to the modulus and theta is equal to the argument. So we still need those elements either to construct the Argand diagram or to represent in polar form, either or. Now let's see how this will look. So we want to express the square root of 3 plus I in polar form. So the first thing that we need to do is we will identify what the modulus is, simply using the basic equation, whereby it will be the square root of x, so that's going to be the square root of root 3, plus the square root of 1, add these together, and then we take the square root, which will become the square root of 4, which is 2. So that tells us the modulus is 2. Now we want the argument. We know the equation for the argument is the inverse of tan with the y coordinate divided by the x coordinate. So it becomes inverse tan of 1 over root 3. This is an exact value, and so it will give us pi over 6. Now it's very, very important to note here is that in polar form and complex numbers, you must work in radians. You can't work in degrees. So please make sure that when you're solving these equations is that your angle or your argument is in radians. And now that we have these values, we can simply pop them in, and we replace r with 2, and we replace theta with pi over 6. So it'll be cos pi over 6 plus I sine pi over 6. And again, you can plot this on a graph, an Argand diagram, and you can visualize what this will actually look like. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept of complex numbers. It gives you a range of different topics, a range of different concepts that will hopefully help in addressing practical problems If you would like to connect with me directly on LinkedIn, then please feel free to scan the QR code, get in touch. If you want any support, if you want to discuss anything chemical engineering wise, then please do feel free to get in touch. Please like and subscribe to the channel if you haven't done so already. It really helps us reach as many students as possible. Thank you for your time, and I look forward to seeing you in another video.